Welcome to the second virtual office hours for the Mobile Cloud course. We have several things we're going to cover today. The first thing I'm going to do is I'm going to go over my solution for assignment number 3, and I'll show you a couple of different approaches there. We'll look at a C++ solution. Actually, we'll look at 2 C++ solutions with ACE, and we'll also look at a Java solution using Nettie. And then we'll also spend a little time going over assignment number 4, so people can figure out a little bit more about how that's going to work as well. Okay. So hopefully everybody can hear me at this point. What I'm going to do is start by sharing my screen, and we will take a look at the C++ solution. Let's see. Here we go. Hopefully you can all see that. If you can't see it, please go ahead and say something about it. So we're going to look at 2 C++ ACE solutions. The first one is very, very simple and probably a little too simple for reasons we'll talk about. And the second one is much more interesting but more complicated. So here is the main program. ACE programs tend to look quite a bit like this in general, the main program. We start out by defining an instance of the reactor, and then we go ahead and we'll define an instance of the acceptor. Make sure everybody can still see this. I think you can. If for some reason you can't see this, holler. And then once we've got the acceptor created, we go ahead and create or open up the acceptor. And when we open up the acceptor, we're going to go ahead and create an INET adder, which is an address structure, and we're going to give it a port number to listen on. And once that is done, and we'll look at what that does in a second, we then turn around and run the reactor. And so henceforth, everything is driven by callbacks. If you watch the videos on ACE Reactor, you'll see something pretty much like this. There's also videos on ACE Acceptor Connector, which you can also look at. Okay, so that's basically it for the overall design. Let's go take a look at the actual implementation that is interesting. Everything else is sort of boilerplate. So we define something called the Echo Service Handler. And as you can see, that Echo Service Handler is an ACE service handler, and it's parameterized by a socket mechanism, a socket class, so it can read the data. That obviously is the wrapper facade pattern right there. This part we're looking at right here is the acceptor portion of the acceptor connector pattern. And of course, the reactors down here, that's the thing that's actually driving the event loop. And then up here on the Echo service handler, we'll implement handle input. So if you watch the video, you'll find out that handle input is what gets called back when something happens that the reactor has been registered to know about. And we'll look more about how that works in a second. So when handle input gets called back, we simply receive a chunk of data, keeping in mind that we're only able to do one receive. You can only receive one thing without having to use the reactor again, because otherwise, if you receive more than one chunk of data, you could block. And the goal of this approach is not to block, at least partly not to block. We'll talk more about that in a second. So we receive a buffer's worth of data. If the values are less than or equal to 0, we bail out, and that causes the reactor to remove the handler. Otherwise, if we didn't fail, we go ahead and we send all n bytes back to the client. So that's an echo example. And I'll talk more about that in a second. Finally, here's the acceptor. As you can see, the acceptor is simply a type def of ACE acceptor parameterized with the Echo service handler, which is the code we just looked at, as well as the wrapper facade ACE sock acceptor, and that creates an acceptor. And the open method of this acceptor will turn around and register this object, in other words, Echo acceptor, with the reactor that's passed in here to listen at this port number. So that's basically it. That's essentially how you could write a very, very simple reactive server with ACE. And naturally, real life, you probably wouldn't write something quite this simple for reasons we'll talk about in a second, but that's very bare bones Acceptor, wrapper facade, and a reactor implementation. All right, let's now go look at this a little bit more carefully. Two things kind of come to mind here. We're going to fix one of them in the next example, and the second thing we're going to talk about we'll fix in assignment number 4. So the first thing to notice is if send n encounters flow control, it will block the server until the flow control abates, until flow control is done. And that, of course, could be a very long time. So we don't really want to have a send end operation because that could block the server. And since there's only one thread of control, that will cause starvation for any other clients that are connected. So we're going to fix that in just a second. The second thing to notice is we're just reading one chunk of data, and we don't even really know if this is, quote, the end of the line. There might actually be a line or a worth of data, and we're just reading a chunk. So there could be some additional stuff that we might want to read. So in the assignment number 4 solution, which we will sketch out today, we will talk about how to do this more effectively. And that involves doing some really clever non-blocking reads to read the line of data in small chunks and buffer them internally until we have an entire line. So we'll come back and talk about that when we talk about assignment number 4. So that was the simple Echo server example. Here's a much cooler example. This is the non-blocking Echo server example. And this illustrates a lot more powerful features of ACE. First, though, let's take a look at the main part of the program. As you can see here, it works identically to what we had before. You declare a reactor, which is the reactor pattern. You make an Echo Acceptor, which is the Acceptor part of the Acceptor connector pattern. And you register these guys via open, which goes ahead and listens on the port number, and then you run the event loop. So that part is identical to what we had before. Also, you can see that the type def of the Echo Acceptor is also identical. So we have Echo Service Handler as a parameter and sock Acceptor as a parameter, and that makes Echo Acceptor. So all that stuff still 100% the same as before. Where things change, of course, is in the Echo Service Handler. And this is going to be quite a bit smarter than the one we had before. Although, as we'll see when we talk about assignment number 4, we could make this even smarter if we wanted to. Once again, Echo Service Handler is a service handler. And so it inherits from service handler and is parameterized by a sock stream. Sock stream, of course, is a wrapper facade, as is the sock Acceptor. Here's the open method. Remember, the open method gets called back down here when the Acceptor is opened. And as you can see, what it's going to do is it's going to basically set the high water mark in the message queue that's part of every service handler. It sets that high water mark to be essentially 20,000 K. So it's a big chunk of memory. And you'll see why we're going to need that in a second. We then turn around and we schedule ourselves to be timed out after 30 seconds. And this is here, of course, in case a client connects to our server and never actually sends us any data. So if they connect to the server and never send us any data, we're just going to bail out after 30 seconds and shut ourselves down. That's a denial of service attack protection. Down here, we set the handler, the underlying handle, rather, into non-blocking mode. So it will be non-blocking. And the last thing we do is then go ahead and register ourselves for callback with the reactor. So we just call up to the parent's open method. Okay. If 30 seconds elapse and nothing has shown up, then the handle timeout method gets called back automatically by the reactor, which also handles the passage of time. It removes the handle and the handler from the reactor, and basically that's no longer there. We're also going to have a method called reschedule timer, and you'll see what that gets used for later. That's going to use to cancel the existing timer and reschedule a new timer. And so those are just some calls that it makes. Here's the handle input method. There's some of this is similar as before. What this does is it goes ahead and reschedules the timeout so that if things aren't handled after a certain amount of time, we bail out again. And then it goes ahead and it receives some data. Now, you'll see again in assignment 4, we'll do a much cooler job of receive. Right now, we make it fairly simple. and we'll look at receive in a second. Receive is going to get a chunk of data, and it's going to store it into something called an ACE message block, which is basically a doubly linked list of message blocks, and each message block is a singly linked list of fragments. And assuming that we read this thing correctly, we go ahead and we put it, and we'll see what put does in a second. Here's receive. The receive method, which gets called back, goes ahead and allocates an ACE message block, and it reads data from the socket into the so-called write pointer of the message block. So it reads the data in there. And then depending on what happens, assuming it was successful, it then sets the write pointer to the end of the data that was read in. And a message block is basically a buffering mechanism. All right, so let's assume we've got data in, it's read in a message block. You'll see later we use message blocks to be much more cool in assignment number 4. And here's the put method. What put does is put checks to see if the message queue is empty. If the message queue is empty, it means that we haven't tried to do a write, or if we did try to do a write, it's succeeded before. So we do a non-blocking put, and we're going to echo it back to the client without blocking the server. Assuming that that works, we're done. Otherwise, if non-blocking put doesn't work, we're going to go ahead and enqueue the message at the end of the message queue, and we're going to tell the reactor to call us back again when flow control abates. And so what we're basically doing here is if the connection is flow controlled, we're going to queue the data up to 200K basically, or 20,000K. And we do this by essentially doing a non-blocking enqueue onto the message queue, which will bail out if it's full. Here's non-blocking put. Non-blocking put attempts a non-blocking send. We'll look at non-blocking send in a second. If that succeeds, then we're done. Otherwise, if it fails because the connection is flow controlled, then we go ahead and enqueue ourselves onto the message queue, putting the message at the front of the queue. And then we schedule ourselves to be awakened when flow control abates at some point in the future. And in either case, when either the first time we send it or when we're awakened again after flow control abates, then we have non-blocking send called, and that goes ahead and does a send operation on the underlying handle. And if it would have blocked, that means that TCP connection flow control was enabled, and so we can't send. Otherwise, if we didn't send all the data in one operation, we update the read pointer, which indicates how much we actually read from in the message, and then we go ahead and redo this whole thing over again. So we'll get called back again when it's possible to make progress. Once everything is finally sent, we go ahead and we release the message block, which basically drains the messages that were allocated dynamically and frees them up. Now, when you register yourself to be awakened, which was what we do up here, schedule wake up, you give the write mask, and that means that the reactor's handle output method will get called back when it's okay to write. And it turns out, unfortunately, Windows and Unix have very different mechanisms for handling this. It's kind of a shame. So we have two different methods, one of which handles Windows, one of which handles Unix. The Unix model basically will keep calling you back as long as the connection is not flow controlled. So every time it calls us back, we basically take the next message off the queue, and we go ahead and try to do a non-blocking put. And when everything works, we're done. And when we're finished, we go ahead and cancel these callbacks. That's how things work on Unix. On Windows, they have a different semantic. This is very, very sad. It's an illustration of why you need wrapper facades and why you need frameworks and so on, because the differences are quite stark. But on Windows, you have to keep writing until you would block, at which point you can then go ahead and get called back again. So the semantics are very different on Windows. So what we do here is we cancel the wake up call as soon as we're called back. And then while we have anything left to send, we send it back to the client. And when we're finally all done again, or when we finally hit the point where flow control is re-encountered, then we can schedule ourselves to be reawakened. The main difference between Windows and Unix with respect to sending data using reactive-like approaches is that with Windows, you tend to make it more difficult to make the sends fair. You have to send everything on a connection until flow control abates, or until flow control is encountered again. Whereas on Unix, you can just basically do one thing at a time, and so you can give everybody else a chance to send their data. So Unix's semantics for this stuff are a little bit more consistent than Windows and a little bit more fair, if you will. Okay, so that's basically the implementation of a much more sophisticated reactive server. And you might ask the question, why on earth would you ever want to do this? And you would do this if you were in an environment where you didn't want to have multiple threads of control for whatever reason. Maybe you didn't want to use the resources for threading because it would take up too much space in your memory, like you're in an embedded system. Maybe it's because you're running on a very old version of Unix that doesn't have support for multi-threading. Whatever the reason is, if you ever need to write a single-threaded reactive server, this program gives you an example of how to do it. It's kind of cool. It's also worth noting, if you were to try to write this code using the native socket API directly, your minds would explode because there's so much platform diversity in this space. Okay, so that's basically the C++ version. Let's go take a look at the Java version. Now, the Java version using Nettie is at a much higher level of abstraction. So in a sense, ACE is more like Lego or an erector set. If anybody remembers what an erector set was, basically it gives you building blocks to put things together, and you put them together, and you have a lot of control over how things are put together. Nettie, in contrast, is much more of a full-featured, higher level framework. And let me show you something here to illustrate this. Let's go back over here for a second, and I'll share something else on my screen to illustrate this. Hopefully I can find it. Let's see, I need to bring up that window. There we go. Now let's try to raise this up. Here we go. So if you take a look at this link here, this is actually was posted on the discussion forum last night. If you take a look up here, there was a good question from Daniel de Leonardis, who talked about Nettie, and he has a link here to a blog posting that explains how Nettie works. And this is a good place to go to learn more about Nettie. So I recommend, if you're curious about Nettie, you go take a look at it. And you'll see when you read this that Nettie is doing a lot of stuff. It's a much higher level framework for asynchronous concurrent network programming with some multi-threading handled down in the bowels of all this stuff. And if you read about the way this works, they have a couple different kinds of threads. They have this thing called the boss thread, which is basically sitting atop of the underlying NIO selector mechanism, which plays the role of the reactor. And some of the code that goes on in the bowels of all that stuff is playing the role of the acceptor. And of course, the underlying Java wrapper facades for sockets and threads and all that good stuff, those are playing the wrapper facade mechanism. And then they have another pool of threads called worker threads. So there's typically a boss thread, and then there are worker threads. And this implementation, by the way, has changed over time. So the implementations have evolved over time. So what's in version 3 is not what's in version 4, and so on. So that's basically how things work. So the bottom line here is that Nettie gives you a higher level framework for doing all this stuff, which is a little different from what ACE is doing. Now, if you really wanted to get experience doing these patterns in Java the same way that we do them in ACE, you'd probably want to use the lower level mechanisms directly. The NIO mechanisms like the selector and Java threads and so on. And we didn't really cover that in this course, or we didn't have that as part of the assignment, just because we didn't teach that material in the lectures, and I didn't want people to pull their hair out trying to figure it out. But that's really the right way to do it. and if you want to get the same equivalent approach that ACE is doing. Instead, we're going to show an approach using Nettie, and basically it implements these patterns. It's just that most of those patterns are implemented in the framework with only a few things kind of popping up at the top of the way you program. So obviously, as I mentioned before, the Nettie API itself is all built upon the wrapper facade and the NIO selector, which is the reactor, and then it's also got implementations internally that handle the underlying acceptor connector logic. So if you go take a look here, here's the Echo server's main program, and basically what you do is you create a socket and you initialize it to receive messages on a certain port, and these are all, like I said, the patterns are implemented underneath the hood, and they have this thing called a pipeline. If you read the blog posting, you'll find out what a pipeline is. And under the hood, there's finally this thing that's called the NIO server socket channel factory, which makes the appropriate threads, the boss thread and the worker threads and so on. And you use this thing, you say new NIO server socket channel factory, and you basically give it in where you want the threads to come from. And it uses the executor mechanisms that are part of Java's executor service framework, which we talked briefly about back in the POSIT class. And then there's a bunch of other kind of low-level calls that you do. Notice we have this thing called an Echo server handler, which is essentially playing the role of the event handler that we get with the reactor pattern that we talked about. And you go ahead and create all this stuff, and you add the handler as the last item on this so-called pipeline, which is a set of processing steps that get done. And then you go ahead and say, basically, go listen to this socket address. And at that point, the server is open for business, and it goes ahead and waits for things to do. And when data comes in, you can see here this Echo server handler is a simple channel upstream handler. And what we do here is there's a couple of callback methods that are invoked to do things. And the most interesting one of them is the so-called message received message, which is basically playing the role of the handle events method in the reactor pattern, or the handle input method in the ACE reactor framework. And when this guy gets called back, he's got the message that came in. And so we go ahead and we grab the message in bytes, and then we turn around and we're going to stick it into this thing called an output buffer. You can see the output buffer is defined up here, big endian heap channel buffer. And once we got the thing in the output buffer, then we check to see if we've got what we want. And if we do, we turn around and we write this thing back to the channel, which is basically the Nettie abstraction for the socket, the underlying socket connection. Of course, it's abstracting away because it's a framework. So that's basically how you could do this kind of thing in Nettie. Like I said, if you really want to understand how the details work, you should take a look at the Nettie source code. The overall approach that Nettie follows is something that's called the half async, half async pattern, a variant of the half sync, half async pattern, which is talked about in a discussion board posting from last night. Okay, so that's basically the Java solution. And now what I'm going to do here is I'm going to go and show you how you might implement the fourth solution with ACE. And I'm going to show you an abridged version of the solution, because I don't want to give it all away. But this will give away some of the key ideas. Some people ask some questions. Evgeny asked the question, can you talk about how to pass things back and forth? So we'll go ahead and talk about that, and I'll show you how that works. Okay, so here is the ACE implementation. Here's my ACE implementation of assignment 4, kind of slimmed down a little bit so that there's still stuff that's interesting to look at. We're going to have a reactor, just like before. We're going to define something called an echo task. We'll look at that in a second. We're going to open up the echo task. That's basically going to be the pool of threads that'll play the synchronous service layer role in the half sync, half async pattern. We then define ourselves an echo acceptor. And then we go ahead and create something called a Echo Service Handler creation strategy, which you'll see what that does in a second. And notice how that includes the reactor and the Echo task. And that, as we'll see, will be used to answer Evgeny's question about how to pass the Echo task into the constructor for the Echo Service Handler. And then we go ahead and open up the Acceptor. And you can see we pass in the port number to listen on, the reactor to use for event demultiplexing, and the creation strategy. This, of course, is using our good friend, the you can have creation strategy, and that's the strategy pattern. And then after all those things are done, we go ahead and run the reactor event loop. Okay, so that's the overall structure of things. Here's a couple things. We're going to define our sock acceptor as an IPC acceptor. That makes it easier to replace sockets with some other mechanism for IPC. We define a port number and the number of timeouts. Now, my solution, of course, as always, uses a pile of other cool patterns, just because I love patterns. And one of the things we're going to show here, this is something I did. Your solution doesn't have to do this, but I decided to do it to make it cool. I defined something called an echo command, which is an ACE message block. And an echo command basically implements the command pattern. And in fact, it's used as part of the command processor pattern. And we're going to use this to pass commands from the async layer, where the reactor lurks, up to the synchronous layer. So echo command, as you can see, gives you back the service handler pointer, and it defines a method called execute. And I'm not going to show you the implementation for that because that really gives away the whole solution. We'll look at that in the next virtual office hours. And basically what it's going to do, of course, is it's going to turn around and send the data back to the client. So it's going to do that. And you can see it keeps a pointer to the service handler. Here's the echo task. This is the guy that is a pool of threads. So we're going to have a pool of 4 threads in this case. You could always change this to have a variable number of threads if you wanted to. We're going to have a high watermark, which is sent to 20,000 K. Here's the open method. This guy is going to get called back automatically down here. The acceptor, let's see, sorry. Here's the open method. This is where it gets called in the main program. And open is going to set the high watermark for the queue to be 20,000 K. And then it's going to go ahead and activate the task to be an active object. And that's going to end up spawning 4 threads in this case, but you could spawn more, of course, if you wanted to. We're just going to do 4 threads. And each of those threads is going to run the service hook method. Here's the service hook method. So each of those threads will call this service hook method. And what this thing's going to do is it's going to go into a loop. And keep in mind, this is running in the async, in the half sync layer, so it can afford to block. It's running in its own thread of control. It's going to block until it gets a command, and when it gets the command, it's going to go ahead and echo the command back to the client. And so it's basically going to get the next command, and it's going to execute it, and that command is going to know how to send itself back to the client. So I left that code out just because that's kind of fun to do. Every task has a method called put, which is used to put messages onto its message queue. And here's the put implementation, which basically just does a put queue, which inserts the command, which is a message block, onto the queue. There's one message queue that's shared by all the threads in the task. Here's the Echo service handler. This is an ACE service handler. It has an enumerated type that keeps track of what state we're in. We can be in one of 2 states. We can either be in a wait to receive more client input state, which is what we do when we have not got an entire message, but we can't afford to block. So we need to use the reactor to call us back when the rest of the message is there. And then there's another state that we're in when we have got an entire message, but there was some additional data that was left over at the end, and we have to kind of put that message fragment and process it before we go back to waiting on the reactor again. So those are the 2 main states that we're in. Here's the constructor. This constructor, as you can see, this is the answer of Evgeny's question about how do we give the ACE task to it. Here's what the constructor does. It's passed an echo task, and this thing is then stored in a local data member. We'll look at that You'll see how this method gets called back in a second, how the echo service handler gets called in the first place. Here's the open method. I'm not going to show you all the implementation here, but basically we set a timeout to guard against denial of service attacks, and then we basically register ourselves with the reactor. This is going to look very much like the open method in the assignment 3 reactor. Handle close is going to get called back when things shut down. We cancel the timer and close down the handle. Handle timeout gets called if the data times out. We basically just go ahead and remove this object from the reactor. Handle input is an interesting thing. This gets called back in the reactor portion by the reactor in the async layer, and it resets the connection timer, and then it checks to see what state we're in. If we need to wait to receive more client input, then it goes ahead and calls receive client input. So it's going to go ahead and use that to get the next chunk of data from the socket. Otherwise, we've got data that's stored in a message fragment, and we have to process that to see whether we've got a complete message. Here's the receive client input method. I'm not going to show that one. That basically is what is reading the data. And what it's doing is it's reading the data in an intelligent way, and it's buffering the data into a message block so that we can basically keep reading until we reach a new line without ever doing more than one receive call at a time to avoid blocking the async layer. Process input basically checks to see if we have a complete message. Again, I'm not going to show that implementation now. Receive message actually gets the next chunk of data from the client. It does a receive and does a bunch of checking. The have complete message is basically the brains that checks to see if you have a complete message. And if you do get a complete message, then it's going to get passed up to the sync layer. If you don't get a complete message, you have to figure out what state you're in and make the appropriate setting before you return. Here's the pass to synchronous service layer message. I put this one in here just because it's kind of cool. This method gets called back once you've figured out whether or not you've got a complete message. So if we now have a complete message that we want to send back to the client, this method is called in the context of the async layer, so it can't afford to block. So we turn around and we make a new echo command, passing the message in, and then we tell the reactor, don't call me back anymore, please, because otherwise we don't want him to get called back until he's done sending the message. And then we go ahead and we put the command to the echo task, and that echo task, as you saw before, will have a pool of threads, and this command will be removed by one of those threads and then executed to send the data back to the client. And then here's the reschedule timer, which essentially goes ahead and cancels timers and stuff like that, and reuses or reschedules them. Here's how you suspend a handler. Here's how you resume a handler. And then here's just the method I used to check to see whether or not we'd reached the end of line character or not, and so on and so forth. Here's some of the state. You can see we keep track of what state we're in. Here's our echo task. Here's our message block. Here's the thing that's used to keep track of the fragment, if we have a fragment, and so on and so forth. And then finally, at long last, I can actually answer Evgeny's question. Here's the creation strategy. And as you can see, its constructor takes a reactor and an echo task pointer, or a task pointer, and stashes it away in a data member. And then when its make service handler method gets called back, we simply say new service handler, and we go ahead and pass in the reactor and the task that were cached in the constructor. So that's how you basically get those things all connected together. So it's pretty cool. Okay, so that's basically a quick overview. You're not at all obliged, of course, to follow this particular model if you do the C++ version. Next week, I will show, after this program is due, I'll show my complete solution, and you'll see how it all works. It's very cool. I will also go ahead and put the implementation of assignment number 3. Let's see, there we go. I will go ahead and put the implementation for assignment number 3 out on the website, so you're welcome to download it and play around with it if you want. It's again, I'll put both the C++ and the Java versions there. By the way, the Java version for assignment number 4 is not that much different from the Java version from assignment number 3. Why? The Nettie framework is handling all the underlying mechanisms for you. So the concurrency model is much more complete from an application end user point of view. So that's great. If you like the Nettie model of concurrency and it works for your application, then by all means use the Nettie model. But if you're programming in another environment, or if you don't like the Nettie model, if you don't like their half async, half async pattern, then you could program it yourself using the lower level mechanisms. Let's see. All right. So Yovoko wanted to know if I'll put the implementation out. Yeah, I'll put the implementation out and send a link to where it is. The message can have more than a single character in it. Yeah, you can do the Nettie implementation all kinds of different ways. You can read it in a character at a time. You can read it in an entire chunk at a time, and it's up to you to decide how you want to do that. There's all kinds of different ways to do it. The implementation is not trying to constrain your creativity in any way, shape, or form. Okay, so if there's any other questions, I will be happy to take them. As I said, earlier, this is a totally optional program. You can do it if you want. If you don't want to do it, you don't need to do it. It gives you a different perspective at a lower layer of the stack than some of the earlier material on mobile cloud computing. Incidentally, it's interesting to sort of ask the question, why would anybody need to know this kind of stuff? And I think it's worth taking a look at the way in which we teach computer science courses in universities to the answer to that question. So if you take a computer science, if you're a computer science major at a university, you take a data structures class where you learn to implement data structures like linked lists and stacks and heaps and queues and so on, and hash tables. Even though you're almost never likely to have to implement those kinds of mechanisms in practice, you'll benefit from learning the concepts of how those data structures and algorithms work. Likewise, if you take an operating systems course, you'll probably learn about interrupt handling and process and thread scheduling and page table layouts and swapping and device driver frameworks and so on, even though very few people ever actually write an operating system. But it helps to understand those concepts because those concepts reappear in other parts of the application world in which you live. In fact, I've actually moved away. When I teach operating system courses these days, I don't really focus as much on the kernel anymore. I focus on concurrency and distribution, because those are really the new generation of management of the concepts that we used to think about in an operating system. But it's still important to understand the concepts. Likewise, if you take a compiler construction class, you'll learn how to build a compiler. You'll learn about parsing and lexical analysis and optimization and abstract syntax trees and peephole optimization and register allocation, all this good stuff. Even though you're probably never going to write a compiler, it's important to understand languages and how to parse and those kinds of things. So likewise, even if you spend your entire career just writing applications on top of some kind of higher level middleware like .NET or Enterprise Java Beans or Spring, it still can be useful to understand the underlying patterns and frameworks for how things work, for several reasons. First, there may be many configuration options your middleware gives you, and knowing how things work under the hood will make you a more effective configurer of those options because you'll understand the underlying trade-offs better. Likewise, not everybody spends their time building applications, although we certainly build a lot of applications these days. There are people who still go off and build infrastructure. And what's really interesting is once you understand the patterns we cover in the POSA material in particular, you'll be able to be much more adept at building that infrastructure effectively. So for example, if you take a look at the Android videos from the POSA course that dealt with the patterns of concurrency and communication in Android, you'll see that all the patterns that we talk about there are basically POSIX patterns. And the same things that we talk about in the context of the JAWS web server also show up in the context of what we're doing with the with Android. And the same thing is true if you look at any infrastructure for cloud computing, or you look at Nettie, you look at Python's twisted environment, you look at C#'s mechanisms for doing networking and concurrency, all those patterns show up in one way or another in those environments. Okay, let's see. A couple more questions. Craig wants to know a few more things about how the Capstone project course will be run. So we have some good news from the Capstone project. Things are a little bit more solidified now, which is good because it starts in a week or so. And basically, a couple things. First, we've decided to move from a 5-week format to an 8-week format, which means you'll have longer to work on the projects. We found as part of the dry run, it was just too compressed trying to do everything within 5 weeks. I think a handful of people probably have got it done in 5 weeks, but 8 weeks should give people more time, even though it will butt up against the Thanksgiving holiday. That hopefully you're not taking 3 weeks off for Thanksgiving. So you should still have a couple extra weeks, even if you take time off during Thanksgiving. Let's see. Sheila wants to know what to do next week for Nettie. Well, again, for Nettie, the basic difference between assignment 3 and assignment 4 has to do with how many threads you want to allocate in order to do the processing. To do things right in a reactive way for assignment 3, you really want to limit yourself to 1 thread, whereas for assignment 4, you really want to increase the number of threads to use. So Nettie makes that sort of drop dead easy, whereas as you can see with ACE, there's more things to be done. And that's because Nettie is a higher level framework than ACE is in that respect. Let's see, is there anything in the course that one has to do to get a so-called distinction? Let's see, I am assuming, so Dennis wants to know what you have to do to get things by distinction. Well, Dennis, let's go take a look. I believe all that information is up on the website, so let's go ahead and take a look at that. If I can get my browser to the right browser to open. Let's see. Is that the right one? We'll see. Yes, this is the right one. So if you go to the obvious place to look, grading and logistics, it tells you exactly what you need to do. So Dennis, what I would recommend you do is go take a look at grading and logistics, and it explains precisely what you need to do in order to be able to get the distinction track and how that compares and contrasts to the normal track. So if you have any questions about that, don't hesitate to ask. But that tells you what you need to do. And I should hasten to note that what you have to do in this class for distinction is essentially the same thing you had to do in the last classes for distinction. You have some additional programming to do in order to get the distinction track. Okay. Does anybody else have any other questions? I'll be happy to hang around another few minutes if anybody else has any questions that they want to ask about in the context of this material. I guess I should also go real quick and see if anybody posted anything on the discussion forums that we want to talk about. Let's go take a quick look there while people are seeing if they have any questions. So here's the discussion forum, virtual office hours for the 26th. And there are a couple of questions. One question was from Daniel, which we've already gone over. He wanted to know about half sync, half async. And I basically pointed to the resources to learn about the different variants of that pattern. And Nettie, I think, implements the half async variant. And then, let's see, Martin wanted to know about the different roles of the patterns, and I gave an answer last night that talked about how things mapped, and we kind of went over that today in virtual office hours. And then there was another question that was asked by Ariel, and he wanted to know how to get access to the peer method from an echo task. And the trick there, let's see, I don't think my solution actually really showed that in any detail, but let me go over here and I will quickly show you the trick to make this work. Let's go back over here and bring up my editor, if I can find it. Let's see. All right. I love Google Hangout, but sometimes it does wacky things with screens that you really want to view. It sort of hides them once you've looked at them. There we go. Now I should be able to share that. All right. So let's go back over here to PA4, and you can take a look at. Oops. So he wanted to know where to get access to the peer. So what I basically do in my solution, I have this execute method right here, and execute is what is actually called from within the task. So if you look at the echo task, in its service hook method, it's going to get the next message out of the message block, and then it's going to go ahead and execute that message. And that execute method, which we see up here, that execute method, if you were to look at the code that I wrote, is going to turn around and forward that to a method on the service handler. And of course, the service handler knows how to get access to the peer, because that's simply this peer in the service handler. So we basically take the message that was passed up through the message queue to the service method on the task, and then use that to be able to execute that message, and the execute then knows how to get back to the service handler, and that service handler knows how to get to the peer handler. So that basically, that's how I did it. By the way, you do not have to do it that way. You're under no obligation whatsoever to follow the same thing I did. That's just answering the question how to do it. That's how I did it. Okay, and question from Craig. There's no requirements to use patterns in our programs. You're welcome to use patterns. The grading will not depend on the patterns, and that's because we're trying very hard to avoid over-constraining the creativity of people. Oh, I should also mention one more thing as well. So in addition to having 3 weeks for the capstone, 3 extra weeks for the capstone, not 3 weeks, 3 extra weeks, so total of 8 weeks, we're also going to have a couple of other projects in addition to Potlatch. So there's going to be one that's going to be from the medical domain, the domain of helping patients who are being treated for cancer to report their pain level based on radiation dosages that they're getting. It's basically a self-monitoring or self-assessment kind of application, kind of cool. This actually comes directly from some people we work with here at the Vanderbilt University Medical Center. And then we're also going to have another project that was given by Amazon, and they specified it, and it basically is going to be sort of a game where you're going to sort of do movie trivia with your friends, try to guess scenes from movies. And then it looks like we're also, knock on wood, going to have another problem or another spec from Google, which deals with kind of helping out volunteer organizations, think like not-for-profit groups or charities or so on, to try to organize people to volunteer to help out on different projects to better the community or to help out people in need and so on. So it looks at the moment like we're going to have 4 different projects that you can use for the capstone, and you get to pick and choose which one you want to have. Derek is happy to see the deadline was extended. You're quite welcome. You know, we were trying to keep this manageable, but you know, it looked like it was going to take a little bit longer than we thought in order to do it. The good news is we should have plenty of material in the actual dry run based on people's feedback and experience from the earlier ones, so we'll be able to point people in the right direction. The other nice thing is that unlike the dry run, where a lot of people hadn't actually finished assignments in the in the Mobile Cloud course, by the time people get to the actual capstone course, everybody should have had a chance to do both of the mandatory assignments in the Mobile Cloud course. So that'll help out a lot, because a lot of what you'll find you'll need for the server side portion of the capstone projects will be very much related to the kinds of things that you did in assignment 2 for the Mobile Cloud course. So I think that'll help you out quite a bit. Okay, well, great. Well, if there's no more questions, I will probably schedule another one of these things next week at some point, and we will go through the solutions to assignment 4. Naturally, as always, if you have any questions, feel free to leave them on the discussion forum, and we will talk about them there. So thanks again very much, and I look forward to talking to you later.